Good looking shirt.
Thank you. At the Getting Place. The best part about it is it's the best shirt for entertaining little kids. Because if you ever find yourself confined with a little kid and you do this, they're like, they know what the hell it is. They're like the worm neck thing. They really just they can't process it. They're like, your face just disappeared. Oh my god! Your neck swallowed your face.
Please, yeah, please start the YouTube video.
Okay, here we go. We're gonna do this. Okay. Oh my god. Special relativity. In a nutshell. No, it's for comparison to general relativity, which is what we're doing. The laws of physics are invariant under transformations. Between inertial frames and space-time is isotropic. And space-time symmetries. Of the Poincare group, P4, ISO 1,3 up, semi-direct product with translation. Okay, so we kind of learned at the end of all of our beating on special relativity that you can really boil it down to a symmetry statement. The symmetries of the space-time and special relativity are different than the symmetries in Galilean relativity. Once you give the symmetry group, though, the statement of the relativity principle is the same. That is, the laws of physics should take the same if you express them in different inertial reference frames. In general relativity, we're going to have a different statement. It's got the same spirit, but of course there has to be something that changes. And so it's going to start with something that is pretty similar. The laws of physics are invariant under diffeomorphisms of spacetime, and we're going to define what those are. But notice I'm leading with an invariant statement. But where it gets different, and this is of course what we should expect, general relativity should have some radically different part from special relativity, because general relativity is way more than special relativity, because general relativity is a generalization of gravity. So somewhere there needs to be something that says, okay, there's gravity in the picture. And the statement is that the connection, which in other parlance we would refer to as the gauge field, facilitating this invariance should be rendered dynamical by the introduction of an invariant field strength tensor, or what is sometimes referred to in particle physics language as a gauge kinetic term. So there's two important parts to the story of general relativity, and for those who took particle physics or who know a little bit about gauge theory in general, it's the same two key ingredients that go into that. There's a symmetry principle. There's a symmetry that you're enforcing. In the case of GR, it's a symmetry, it's an invariance under diffeomorphisms. These are a larger class of transformations than we consider in special relativity. Okay, But that's not all. It's not enough to just say, I want my theory to be invariant. You find that to create that invariance, under these very general transformations, you end up having to introduce something called a gauge field. This is the same thing you do in quantum electrodynamics or any gauge theory. But when you introduce that gauge field, you want that gauge field to be dynamical. You want it to be able to propagate and have interactions. And to do that, you have to introduce a gauge field kinetic term or some field strength tensor. And it's this second part that gives us the dynamical gravity. It's the thing that actually says space-time, its geometry is actually dynamically determined in response to sources. So we're going to see, like, I don't write this expecting you to look at it and go, yeah, I get that. But I'm telling you, this is the program that we're going to spend the rest of the next few weeks leading up to spring break really fleshing out. But there is a direct analogy to what you do when you're developing gauge theories in particle physics. And so there's a really nice parallel. Okay. Jesus. There's a lot of text on here. Like, what? How do I expect to teach like a class with those being my notes? Like, I can't do that. So I gotta stand here and read the paragraph and then decide what I'm going to tell you.
Yeah, you could be in that time. You did.
You guys get that? Well, I'm going to put these on the right anyway. I don't need to do that. I don't know. This is all crap. I'm sure it's important. Okay. Anyway, read it. Read it. It's important. All right. There's like all these motivational words.
You're not
Okay.
going to read it?
No, I'm not going to read it.
You should just read it out loud and we'll absorb it.
Okay. Yeah, because that's the way learning happens. Here we
Yeah,
go.
I'll read it and you go to the bathroom.
Oh, that would be so awesome. But no, then I'd really be. Wait, we weren't going to talk about that on camera. Now the world knows I have to pee. And now if I go to the bathroom, imagine what's going through my head. Oh my God, that would be terrible.
You gotta get out of your head.
Dear
Can't just go to the
God,
bathroom.
no, we're not, forget about me going to the bathroom
I found it a lot easier.
ever.
We care so much about others.
All right, here, I'm going to read it really fast. Here we go, because I know there's something in here I need to say and I'm forgetting to say it.
Just go to bed and don't read it.
No, I'm going to read it. I feel so bad. It will. No, I'm literally going to read to you what I write on my notes. This is so dumb, but I'm going to do it. It will take time to digest all of this, especially the second half. But the first half. Okay, yeah, no. So the first half is going to look a lot like no. So what we're going to do is we're going to do a lot of stuff that's going to look exactly like what we did for special relativity, in the sense that we're going to have to go back and we're going to have to carefully define what a vector is, how a vector transforms, define a dual vector, how a dual vector transforms, define what a tensor is, how tensors transform. We're going to repeat all of that with a slightly more sophisticated machinery, because we're going to need that extra machinery for curved space. That's going to look very similar to what we've already done. The second part of what I wrote up here, which is introducing an invariant field strength tensor, that part is going to look new and glorious, and it's not going to look like anything that we had to contend with in special relativity for obvious reasons, because special relativity did not have gravity. Okay? All right, I'm not going to read this. I'm just going to go on. Screw it. Okay. So reminder quickly of what got us to where we are. There is the Einstein equivalence principle, which says in words, actually I'll just let somebody repeat it for me. Oh, Hunter, you're up. Remind me, what is... Say it again? Absolutely. Tell me what the Einstein equivalence principle says in words.
For any objects and any forces except internal gravitation, a uniform external gravitational field is indistinguishable from a uniform acceleration for a small lab.
Spoken like you do not have to go to the bathroom like me. Okay?
Now I'm just talking about it. You want us to play like waterfall sounds?
Okay, so I love picture math, so we're going to do a little bit of picture math. So the Einstein equivalence principle says that a lab at rest, and maybe I should do it this way. A lab at rest in the presence of a uniform gravitational field is equivalent to the physics in that lab, as long as that lab is small enough and the duration of the experiment is short enough in time, is equivalent to the physics in a similar lab with no gravity, but which is being accelerated uniformly in the direction opposite, where the magnitude of this is opposite the magnitude of the universal gravitation. And then you can do picture math. You have an equation, there's an equal sign, that means you can move things back and forth, which means if we take a lab in the presence of G, and we allow that lab we subtract from it this, right? So I'm going to take this and subtract that. What should I get?
0.
I should get 0. So that's lab. Okay? But of course, subtracting this is the same as adding this. Right? That's how we do vector subtraction. We add the negative vector. Okay? But this is picture math. All this says is, if I have gravity and I allow my lab to fall off a cliff, the gravity disappears. So it's a way of getting rid of gravity. And this is how we arrived at our best inertial frames are freely falling ones.
Did you make the O a heart because it's Valentine's Day?
Smart.
Okay. All right. So there are two important implications of this Einstein equivalence principle sort of being our seed for getting into general relativity. One is, of course, that if we allow ourselves to go into a freely falling frame, or what we'll think of as an inertial frame, then we should expect the resulting physics to look identical to physics in deep space, where the notion of deep space is that you're very, very far away from any gravitational sources. Okay, so it's literally like pure floating space. And then the second implication which we ended with last time was that if we're trying to look for what spaces are relevant in general relativity, because after all, you all know this is going to be a theory of dynamical space-time. The space-time can be warpy, bendy, whatever. If we're trying to figure out, well, what are the sort of broad characteristics those spaces must exhibit, the one thing we know is that there should be some sense where if you go to a small enough region, the space should be locally flat. That's exactly what this is saying. If you go to a small enough region, that's a small lab over a small time interval, and you do allow yourself to be in free fall, your experience of that space-time should be as if it's flat. That is a space-time without gravity. Flat means no gravity. Those are interchangeable. Okay, and then we said that's sort of the motivation for the notion of manifolds, and that's what we're going to start studying intensely today. So before I launch into the very heavy math of manifolds, I'm just going to give you some notation or nomenclature because I might say a few things, and I want to be clear what I mean when I say it. So we know that there's a couple of very special metrics. And we have for the case where we have a spatial metric, which is just the identity, or we have a spatial metric, which is -1, and then the identity down the diagonals. And here we're talking about Euclidean space. And this is in rectangular coordinates, because as I mentioned last time, if we go to polar coordinates or some curvilinear coordinates, even though we're working with flat space, in curvilinear coordinates, the metric that you have to use is different. So this is only the metric in Euclidean space in rectangular coordinates. And so too in the case of special relativity, this is the metric of Minkowski space time Again, only in rectilinear coordinates. Okay, if I change coordinates, the form of this metric can change. Okay. Now, the new pieces of notation are that I'm going to consider a Riemannian metric. And a Riemannian metric is one where I doesn't have to take either of these special forms. But if I have a metric where all of the diagonals are positive, okay, then we have what's called a Euclidean signature metric. That is, it's roughly in the same category of metrics as this. This has all positives down the diagonal. It's spatial. Once we start screwing the metric up, either by choosing weird coordinates or actually looking at curved geometries, we can still ask, is it somehow a spatial geometry or is it a space-time geometry? And the way we figure that out is we can just look at the sign of the things on the diagonal. If we're dealing with a purely spatial geometry, the sign of everything on the diagonal should be positive. If we're dealing with a space-time, then we're technically dealing with a pseudo-Riemannian manifold or a pseudo-Riemannian space where one of these will be negative. We can just, by convention, take it to be the leading one. And then we have what is called a Lorentzian signature space-time. So when I use the words Euclidean signature or Euclidean manifold, or I use Lorentzian signature or Lorentzian manifold, this really just means spatial, and this means a space-time. I say this because even though we're doing general relativity, which is the theory of space-time, a lot of our examples of like curved spaces will just be spatial. Like I'll draw a sphere, that's like not got time in it. So we will find ourselves quite often developing tools for Euclidean geometries or Euclidean signature geometries, I should be careful, along the way to formulating things that we can use on Lorentzian signature. And I need to be careful because if I say Euclidean space, I'm talking about this. This is not necessarily Euclidean space. This can be a curved space. But we can recognize that it is spatial because it has this Euclidean signature. Yeah, go ahead.
Can those things down the diagonal be functions?
They could be functions, yeah.
Have we moved away from like spatial as letters and the space-time as Greek letters?
No, that we're still going to be doing that whenever we need to. Yeah. Okay, so without any further ado, let's talk about a manifold. What is a manifold? Okay, so here we go. A CP manifold, CP n-dimensional manifold is a set M with a maximal atlas. That's it.
See you next week.
Do you have a
Yeah, you
quiz
just
on
want to go
Tuesday?
to that.
Right. Well, there you go. I mean, that's what we said we were going to talk about today. That's what it is. So, are there any questions?
How's your week been?
Pretty good. Very good. Yeah.
What is a maximal atlas?
Exactly. So no, I mean, obviously, like, these are all $2 words, so I got to go back and dig into these. So we're going to go through these one word at a time. And we're going to have to talk about a lot of different ideas to get there. So what does CP mean? What does maximal mean? What does atlas mean? Okay. So first of all, the set M. Now the notion of manifold and the important properties of manifolds extend way beyond general relativity. You can, these ideas extend into lots of branches of math and even physics. But for our purposes, the set M we have in mind is a collection or the collection of points in space-time. Okay, so a set in the most abstract thing is just a collection of stuff, like it's a collection of things. And what we're talking about is the collection of distinct points in space-time. That's our set. Okay? Now, I'm not saying anything about coordinates yet. I'm literally just saying there's this thing we call space-time, and I can point to different points in it, and all those different points I can point to is my collection, my set. Yeah.
So it doesn't, I don't know, I can ask that question later.
I didn't understand anything you just said. Okay. All right. So what we're going to do is to sort of organize and dig into the rest of these words, what we're going to do is we're going to take our set, which I'm just going to kind of draw by this big box. Okay, so that's space-time. I don't have the time or energy to draw an infinite space-time, so this can be infinite if you like. And this set M is, in general, going to be n-dimensional. Of course, in the end, we're going to be interested in this being a 3+1 dimensional space-time, but to get definitions that apply to like two-dimensional spatial geometries, which are nice and easy to draw, let's just kind of do our definitions in arbitrary dimension. And then what we're going to find convenient to do is to take this set and to break it up into chunks. Okay? So I'm going to just start drawing blobs. And the important thing in drawing these blobs is that at the end of this procedure, I need to make sure that I've drawn blobs such that I have accounted for every single bit of them. Okay, and these blobs can and actually need to overlap. Oh my God. I think I got it all.
There's that little
Top
top
right
right
corner.
corner.
Screw you guys. Oh yeah, you're right, you're right. I saw it. I was like, there's no way I'm going to find the part I missed, but you're right, it's that corner. Okay, this is horrible, and I'm never going to draw that again. So I'm going to draw a slightly easier to digest version of that, which doesn't satisfy that, but just imagine that I do. So I'm just going to imagine drawing a couple of blobs. Okay. But I'm going to cover the entirety of this set with these. So I'm going to give these names, call it U1, U2, and then we'll have U3, U4, U5 for all of these different things. Okay, the U alpha are called charts. Okay. And let me give you a concrete definition of a chart. A chart is a subset of the set M. And it's not just a pretty little blob. There's actually a technical thing that goes on with the chart. With a 1-to-1 map, phi from the chart into Rn, and there's more, such that the image of phi alpha is open in Rn. Okay, so this notation here, when I write it like this, okay, what I have in mind is that this map phi alpha, so if I'm thinking about the map associated with this chart, so if this chart is U1, it will have a map phi 1. What it means is I can take a point in that chart, so this is a point inside of U1, and I can apply that map, and that map phi 1, and I shouldn't write that, I should actually draw the arrow. That map phi 1 takes this point and gives me a corresponding point in Rn. So the map is really, it's a map. It takes you from, right, that's not what a map does. A map is a picture of lines and shit. But anyway, in math land, a map is like a function. You feed it something and it gives you something back. Okay, in math, high enough in math, all you talk about is maps. You just never really care about functions. They're just an example. So everything, mapping, mapping, mapping. Okay, yeah, go ahead.
Is there a reason why we want the image to be open?
We're going to talk about all that. So I'm going to define these words for you now, these underlined words. Yes?
So when you say Rn, does that also imply, like, when we're working with a 3 plus 1 dimensional, like M, set M, is that R 3 plus 1?
Mm-hmm. Yeah. And I'm going to explain to you the significance of Rn in just a minute. Okay. So let's go back and let's talk about what some of these underlined words mean, because I don't want to assume that everybody has familiarity with a bunch of math terms. So one-to-one, many of you might be familiar with this. Good God, heaven above. Is also called an injective map. And what we have in mind is the following. If I take the set if I take U alpha, the alpha chart, and I take 2 points, A and B, and I consider their image over here in Rn, then A gets mapped to a point over here by the map phi alpha, and B gets mapped to a point over here. So this might be A prime and B prime by the map phi alpha. And you might have a point over here, C prime, which doesn't come from a point in U alpha, okay? But this is a sort of a pictorial representation of what the word injective means, or what one-to-one means. So to really drive the point home, let me contrast it with other possibilities. So we could imagine that our map takes A and B to the same point. Okay, so it might be that I take 2 distinct points in U alpha, but when I apply the phi map, they actually end up at the same point. I don't even know what to call this. A prime equals B prime, I guess. Okay? This is what is called a many-to-one map. Because you have many things that get mapped to the same object. Okay? Of course, the converse of that is if I somehow started with a single thing, but somehow, by some magical mysticism, this got actually mapped to 2 different points, this would be a one-to-many map. Okay? So clearly, one-to-one means what the words say. It says for everything here, there is a unique destination over here. Okay? Now there is a way that you can enhance this, and that is to say if we take one-to-one and we add surjective, which is called onto. Now what this means is that surjective or onto means that if we start here and we grab all of the points in here and we map them, if it's an onto map, that means we actually reproduce all of the points over here. In the current picture, that's not happening because the idea of this C prime is that this is a point over here which you actually don't get from something over here. Okay? We do not require both of these. We only require this one. However, just to give you an idea of how this works, if I were to require both one-to-one and onto, then I get a very special class of maps that are called, any takers? Bijective. Those are bijective. And what do you think is the important property of a bijective map?
It's surjective and injective.
Yes.
Doesn't like get rid of anything.
Yes.
Has fun.
It's invertible.
It's invertible. This map actually has a well-defined inverse. Notice an injective map doesn't, because I can't ask what's the inverse of the map on C, because this doesn't come from anywhere. Clearly, many-to-one and one-to-many maps are not invertible. Okay, so I need one-to-one, and I also need everything over here to come from the mapping in order to be able to say this is what the inverse map is. We do not require that for our definitions. We just require one-to-one. We don't actually require the invertibility criterion for these maps. Okay, remember to draw some cards. Okay, so any questions about what one-to-one means? All right. Open. Open in Rn means the interior of an n-1 dimensional closed surface. Okay. So as an example, that is a, actually, these points are a zero-dimensional closed surface in R1. That's the endpoints of a line interval. The endpoints themselves are zero-dimensional. Okay. If I take the interior of that closed surface, then I'm thinking about the line interval without including the endpoints. Okay. This is open in R1. Yeah. So many, I mean, there's higher dimensional generalizations of this. So clearly, you know, one obvious example is if I take the surface of a sphere S2, say with some, you know, radius r, and then I set up an x and a y, and then I take all x, y, and z such that x squared plus y squared plus z squared equals r squared. That's the surface S2. That's the surface of the sphere. However, if I take all x, y, and z such that the sum of their squares is less than r squared, then I'm talking about the interior of this, but not including the actual surface. That's open. I can take the interior and include the surface, and then that's closed. Yeah.
Is this condition y, m, and u are sets, not groups? Because they're open, not closed?
Why they're sets and not group? Well, I haven't given you,
Oh,
to promote it to a group, I have to give you some composition on
Okay,
it.
okay.
Means of taking elements of the set and combining them to
Okay.
produce elements of the set. Okay, so really, you know, what's nice? The thing that you should think of that's nice about an open set is that if you're a little ant and you're crawling around in here, if you are restricted to live in the open set, then you never really hit the wall. You can crawl around all these x and y's and z's, and you can keep getting closer and closer and closer, but you never actually hit the wall. Okay? However, if you're an ant that lives here, then you're allowed to crawl to the wall and sit on the wall and go, wow, wall. Okay? So mathematicians probably have an intuitive way to get you to think about this, but There's a sense in which when you're dealing with an open set, you can keep going and there's not like an obvious stopping point. You know, it's the whole, is it Zeno's paradox? Where you walk halfway to the wall and then you walk halfway and then halfway and halfway and you never get to the wall, but you're always walking. Okay, it's just that same idea. Okay, everything between you and the wall, when you don't include the wall, forms an open set, and then you can just keep moving in that open set. But as soon as you include the wall, you can smack into it and your journey's over. Okay, yeah.
Could you ever be closed in Rn since it's infinitely big? Like, why do we have to put that qualifier on it?
Open in Rn is the interior of an n-1 dimensional closed surface. Ask your question one more time. I mean, you can take Rn itself is open.
Yeah.
So you can take Rn itself.
Yeah.
Sure. So yes, there are open sets of Rn that are not the interior of an n-1 dimensional closed surface, but I think those are isomorphic to Rn itself.
Is the fact that they're open why they have to overlap?
Yeah. That gets into a weird. So we've had this question before when I taught this class, and so it was this question of, do you have to have them overlap, or can you just somehow have them abut each other perfectly? And if they abut, so like literally if their boundaries between two different charts are shared, and you do this and you manage to sort of tile the whole space with these kinds of shapes, haven't you covered the entire space? And the issue with that is, that so I mean, I mean, first of all, to your point, like, if I do this, the only way that the point that actually is on this, where these come together, the only way that that's included is if these include, well, no, that's the map that has to map to an open subset of Rn. The charts themselves can have boundaries. I don't know the right way to answer your question right now.
Okay.
But let me go, so there's a point where I'm going to take all this machinery and connect it to something you're very familiar with, and then we'll end with an example, and I think those kinds of questions might be better saved until the end, because I might answer them along the way, but right now you can ask me lots of technical questions that I don't have good motivational answers for.
Right.
So let's actually see how the story plays out. And I have to say, like, you can beat on this structure and do a lot of interesting mathematical things, but that's not necessarily going to be of relevance for this, for our purposes of what we need manifolds to do in general relativity. Okay, so, all right. So we've basically got the word, well, we actually haven't talked about any of the words here. Well, we talked about a set, that's progress. But no, we've got charts, but we haven't got the rest of this. Okay, so the notion of a chart sounds abstract. Like there's a lot of really highbrow, sophisticated language here. But this notion is actually something that you've been doing forever. You did it the first week of Physics 1. Okay, this map from points in a space to elements of Rn has a name. It's called setting up coordinates. The coordinates are values in Rn. But what they mean to us is when we have a space and we set up coordinates in that space, which says now, if I pick a point in the space, that means a value of x and y. All we're doing is we're not drawing x and y on the space, we're drawing it over here, and then we're drawing this funny arrow that says take this point and deliver me to a point over here. That's all we're saying. And you'll understand the reason for that in a few minutes. Among it, though, is the following idea. So let me draw a picture, a concrete example of this that you're familiar with to illustrate why we should really separate those two. So, so let's take a space we're all very familiar with, and that is the sphere. If I pick a point on the surface of the sphere, then we can identify the location of this point in different ways. First, I could set up x, y, and z coordinates, but that's almost overkill because it's a three-dimensional coordinate system for a surface that's two-dimensional, right? We don't need 3 coordinates. We could just do 2. So you all know what you can do. You can talk about the polar angle theta, and then the azimuthal angle phi. And so for any point on the sphere, if you tell me the polar angle and the azimuthal angle, then I know which point you're talking about. Okay? So theta and phi are coordinates for a curved space that take values in R2. Literally, that's the way we think about theta and phi. Okay? This space is not the space of the sphere. And yet, we can pick any point on the sphere, and then using a map, which we never really formally wrote it down before, but using this map, we can map it to a point here, and we can say, okay, the pair right there, given by the ordered pair theta and phi, is the image of that guy right there. Okay. So when I give you all this fancy hoo-ha about charts and one-to-one maps and all this fancy stuff, all I'm saying is I want on each chart to be able to set up coordinates. That's it. Okay? And I think you're all well aware of the significance and value of coordinates when trying to do mathematical treatments of physics.
With the map there, like the transformation between rectangular coordinates and spherical, where you get rid of the...
No. So so that's a very interesting question. So coming back to are we talking about a transformation from spherical to rectangular coordinates? I'm not saying that. Like, obviously, when we think of Rn, we're naturally inclined to think of rectangular coordinates in Rn. But these are just labels. Like, I could label them theta and phi. Okay? I'm going to, in just a moment, make a connection to how you would talk about going from one set of coordinates to another set of coordinates. I'll talk about that in a minute. But I am not trying to say that I have some sort of curved coordinates and this map is making them into some rectilinear coordinates.
I would assume the opposite. Because isn't the sphere live in a rectilinear space, like the way you do it with the coordinate?
Oh, you're talking about if I somehow take those coordinates and relate them back to x, y, and z in the rectilinear space? Well, we don't need to go there. We don't need to go there. So I just want you to have 2 separate ideas in your head. One is the actual space you're working with, And then there is this sort of auxiliary thing. It's always copies of Rn, which are just perfectly flat Euclidean spaces. And that's what's important. This is a curved space that you're always mapping to Euclidean space. And the values in this Euclidean space are just your coordinate values. But they are associated through the map to distinct points in the space you're starting with. Okay, and so let me beat on this a little bit more and then come back to coordinate changes. Okay, so now that we have this rough definition of what a chart is, let's talk about an atlas. So an atlas on a set M is a collection of charts so the curly just means it's a set, and the elements of the set are the patch and the map. So each chart comes with its own map. So that's why I have the index alpha on U and phi. And then the set is a bunch of these. So we could imagine, we have U1, phi 1, U2, phi 2, et cetera, et cetera. Okay, so that set is an atlas such that A, the union of all charts, is equal to M. And this is what I was saying earlier. I want to draw enough of these charts so that I cover all of the M. That way, if I consider the collection of all of the charts together, that's their union, I've covered all of them. Go ahead.
Do they have to be equal to, or can they just include M? So bigger than M.
Oh, it would be, I'm trying to think of an example where it could be larger. Because we're not going to talk about manifolds with boundaries.
Okay.
So here, it's obvious that I could draw a chart that kind of goes off the edge of M. But first of all, this doesn't exist. M is the only thing that exists.
Okay.
So I can't even really draw this. And then the fact that there's a boundary here might upset you because you're like, well, what does that look like? But we're not going to have boundaries on all our manifolds. So So I don't think that that's really a concern. But I don't know. I mean, there could be some really weird, wonky thing where that happens. Okay, and then the second part, in order for this to be an atlas, is that the charts are sewn together with CP transition functions. Okay, so I did it again. I defined something in terms of things that need to be defined. I'm getting good at that.
Yeah.
Yeah.
How can you be equal to M if M has no boundaries? Like, what does that mean?
Let me defer that to the explicit example that I'm going to do at the end. I'm going to do a very concrete example where every single word that I'm using is going to be brought into concrete terms in the example that I'll do at the end. But let me now define the underlying word CP transition functions. And this is where this gets cray-cray, but bear with me. I love this picture, but it can be very intimidating. So here we go. So criteria A is just I want to cover the entire space. Criteria B are that the charts are sewn together. So what we have in mind here is we're looking specifically at the overlap between two charts. So I'm going to have chart 1 and chart 2, and then I have this overlap region, which is the intersection of chart 1 and chart 2, which I will notate properly. as I did not in my physics X lecture. Okay, and now I'm going to draw this really crazy picture, but it'll be pretty easy to follow once I get all the stuff down. So first of all, we have two patches of Rn to work with. Why do I have two patches of Rn to work with? I just draw some cards, man. Chase! And Chase in. He always gets me because he's got Chase Bank. But then he put the N in. Jason, why am I going to have two patches of Rn to work with?
Because U1 and U2 each are.
Yeah, exactly. Each of these U1 and U2 come equipped with a map into Rn. There's no reason why they have to be the same Rns. In fact, we don't want them to be. So this might be the Rn that is associated with the map phi1, and this would be the copy of Rn that is associated with the map phi2. Okay?
Is N necessarily equal?
Yeah, so this is the set M is n-dimensional, and the copies of Rn that you're mapping into have, or sorry, yeah, it's n-dimensional. So the dimensionality of everything has to agree. You asked that, right, Alex? Okay, yeah. Okay, so here we go. This is where it gets real. You ready? So I'm going to consider a point in this copy of Rn I'm going to call P1. I'm going to call a point over here P2. I'm going to, for the moment, erase these because we will get very confused by them because this picture is going to get really crazy. And here we go. I'm going to consider a point P. And now I'm going to consider the following equivalence. P1, that's this guy, is equal to phi1 of P, which is equal to phi1 compose phi2 inverse of P2, let's actually see that this makes sense. So P1, what I have in mind is that this point P1 is what I get when I take this point P and I map it with the phi1. That's the map from this chart. Okay. I can do that to this point because this point is contained on U1. Right? However, since this point also belongs to U2, I could imagine getting this point by applying the inverse of the phi2 map to the point P2. Yes?
So this set's 1 to 1. Is the transformation backwards?
That's a very interesting point. So what right do I have to talk about phi2 inverse? Okay? So the thing is, the map from here to here is 1 to 1. Okay? So what that means is that there could be points in here which do not come from points in here. And if I take all of the points over here, there's not an inverse. But if I only think about the points in here that come from points in here, then I have an inverse because it's 1 to 1. And if I'm only considering the points that come from here, then it's on 2. Okay? So because I'm thinking about a point in here that came from a point in here, because remember the phi2 map does this, then that has to have an inverse. Okay? But that's a really good point. Okay? Now all that this statement says is this sequence of maps. So you start out with the thing that's kind of nested the deepest in parentheses. So I start out with P2, and then I act on it with the thing that's closest to it. So I act on it with the phi2 inverse that carries me to this point. But then I take that point and I act on it with phi1, which drops me down to here. So at the end of the day, this map is a map from that point P2 to that point P1. Okay? Now the transition function is just phi 1 compose phi 2 inverse. That is, the transition function that I'm talking about up here is literally a map from points in one Rn to points in the other Rn, where these sets of points are relatable as coming from the intersection of two charts. Notice, none of this would make sense if I picked a point here, right? Because I could take this back and forth to here, but I have no way to take it to here. It's got to be on the intersection. That's where the money is, okay? Now, let's just think for a moment about what this would look like. I'm literally taking points in one Rn, which I'll call the 2 copy of Rn, and this is the 1 copy of Rn. I'm literally taking points here, and I'm creating a map to points here. Well, I can write down what that map would look like in general. It would look something like this. If I chose rectilinear coordinates, on each copy of Rn, all this is saying is, okay, if this point has some coordinate values, x1, y1, z2, whatever, or x1, y1, z1, blah, 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 blah. And this point in this coordinate system has values x, y, z, but x2, y2, z2, etc. Then you give me the x, y, and z values of this point, and this transition function lets me construct the corresponding x, y, and z values of this point over here. Now that is just hoity-toity language for what? That's a coordinate transformation. These transition functions are nothing but coordinate transformations from one set of coordinates, because remember the coordinates live in these Rn's, they don't live in the space itself. The transition functions are just coordinate changes from one set of coordinates to another. Now with that in mind, I didn't necessarily have to choose this one to use x, y, and z. I could have chosen to use phi and theta and some angles. And so this same kind of transition function would now represent transformations between, curvilinear coordinates and rectangular coordinates. Yeah?
Can you say because the map of R1 to the union, to the intersection is onto, and the other one is onto as well, that the map from R2 to R1 is also 1-to-1? Sorry, it's 1-to-1, not onto. Because one map is 1-to-1 and the other map is also 1-to-1, the map from all the way to 1-to-1?
So the answer is, the answer to your query is, can we necessarily say that that map is onto? And the answer is no.
Yeah, sorry, and I meant 1-to-1.
Oh, 1-to-1,
Yeah.
yes.
Okay.
Something 1-to-1 times.
Not necessarily. Not necessarily. It might not be. Yeah, so you got to be a little bit careful because you could have a degenerate map. So for example, we know in spherical polar coordinates, if you go to the polar angle being zero, or the polar angle being 0, then all values of phi correspond to the same point. So you got to be a little bit careful.
Okay.
But I am going to add in that layer of qualification to our final definition. So no, this map here need not be one-to-one.
Okay.
Because we can have these sort of degenerate coordinate transformations, which you've encountered before.
Yeah.
Okay, so we're really close to understanding all these words. Let me put the final definitions down, and then we'll just look at how all this appears in a concrete example. So I got an atlas, I got this, CP I haven't talked about, so let's talk about CP for a moment. So the good news is that transition functions are now maps from Rn to Rn. But guess what? You all are experts in maps from Rn to Rn. This is what you spent most of your math career studying. Okay, this is the setting in which you do calculus. Talk about functions, which are essentially maps from Rn into Rn. And so what that means is that we can now start talking about various ideas of calculus. So in particular, we can talk about differentiability. And so we can say that if the pth derivative of all transition functions, which I'll call phi alpha beta, because this transition function obviously has to have two labels for the two charts that are intersecting. So I can just call this whole thing phi alpha beta, where you can imagine that the second one is the one where we use the inverse map, and the first one is the one where we use the original map for the chart. If the pth derivative of all the transition functions, phi alpha beta, exists and is continuous, then phi alpha beta is CP. So the word CP just means, so first of all, CP is saying something about a transition function. It's saying something about a map. And all it's saying is that the pth derivative of that map exists and is continuous. So let me give you a concrete example of what I mean by this. So let's suppose that I handed you a function like this. Okay. What is the degree of C-ness to this? Is it C1, C2, C3, C12, C4 and a half?
0.
It's C0, right? Because if you take the first derivative of it, you get a discontinuity. So if you map the first derivative of this thing, you'll find a positive value, and then it immediately jumps to a negative value. But these two things aren't connected, so this is discontinuous. So this would be an example of a C0 function. A C infinity function, well, that's pretty easy. These are actually what you tend to deal with. So for example, a sine curve or a cosine curve happens to be what I drew. You know that you can take as many derivatives of this as you like, and you keep getting continuous functions. Okay? Examples that might not be as obvious. What is the p-value for that function? It's infinity. You can take two derivatives of it, but the third derivative is automatically 0. But you can take the derivative of 0. It's 0. Okay, so just because things hit a constant doesn't mean you can't take derivatives anymore. Okay? Last but not least, I'm running out of space. I'm going to start erasing. And this comes back to your point. If phi alpha beta, that is the transition functions, If the phi alpha beta are C infinity, that is, they're continuously infinitely differentiable, and invertible, then phi alpha beta is called a diffeomorphism. So that was a word that I actually threw out when I was talking about sort of the symmetry underlying general relativity. It's based on diffeomorphism invariance. Okay. So a diffeomorphism is just a particularly nice set of these transition functions, which are really like the kinds of functions you've studied forever. You know, sines, cosines, polynomials, things like that. So they're invertible and continuously differentiable. Okay, the last thing we need to say is what the word maximal means. So notice here in our original definition, we've got CP, we've got a set, we've got what an atlas is, and now I just need to tell you what a maximal atlas is. Okay? And this is probably the weirdest of all, and not one that you actually will think too hard about, fortunately. But essentially, the idea of a maximal atlas is the following. Imagine that you have a space M, and I'm just going to draw it twice. And over here, I cover it with some atlas of charts. And then over here, I cover it with a different atlas of charts. Okay? Now, all of these charts are going to satisfy all of the conditions. You'll have transition functions, which are CP, if you want this to be a P, smooth manifold. But here's the thing. At the level of defining things, if I define this thing as a manifold through its atlas, then this is different than this, because these are different atlases. And notice, like up here, a CP n-dimensional manifold is a set M with an atlas. If I left out the word maximal, I'll tell you what maximal means in a second, then you might be led to believe that if I use two different atlases, I'm talking about two different manifolds. We don't want that to be the case. We want it to be the case that it doesn't matter what atlas you choose. As long as you're choosing an atlas that satisfies all of our criteria, then you should be defining and talking about the same underlying manifold. So what the word maximal says is, we are going to consider an equivalence class of atlases. And what an equivalence class means is simply, it's a set of atlases that you identify as all corresponding to the same thing. So you can imagine taking every single possible atlas you could imagine to cover a manifold. That collection is the maximal atlas, that you only ever need to work with one of them, because they all define exactly the same space. We'll never need to consciously think about that. We'll just say, I just want to get an atlas. But we always bear in mind we could have done a different one, and we're still talking about the same space. Okay. So I'm going to very, very quickly bust out a concrete example, because this is where all of these ideas really come to, they kind of congeal. And the hilarious part about this example is that 2 iterations of this course ago, I gave this example, and I literally, so those of you who have seen my Failure Friday video knows the story. I literally just totally screwed the pooch. Like, I screwed it up so bad. I was trying to do things which were counter to the very definition of what I was trying to achieve. So I feel like I have to do this and do it right in order to be worthy of standing here in front of you. So what we're going to do really quickly is prove that S1 is a manifold. And it's going to bring to bear all of the definitions that we've just given. So S1 is probably one of the simplest spaces. It's a circle. So that's good old S1. And now, S1 is a one-dimensional manifold, obviously. Remember, we're just talking about the surface of the circle. We're not talking about what's inside. It's one-dimensional. Now, you might think that if I was going to cover this with an atlas, that my atlas could just have one chart in it. And sometimes we can do that. Sometimes we can cover a space with a single chart. okay? But it turns out you can't cover S1 with a single chart. You have to use a minimum of 2. And you can try and do it with 1, and you'll find out very quickly that it's not going to satisfy all our definitions. So I'm not going to prove that to you, I'm just going to use 2. And in the process of using 2, you'll probably see why you couldn't have just used 1. You can use more, you can use 3, 4, however many you want, it doesn't matter. But 2 is the minimum, all right? So in order to choose 2, what I'm going to do is the following. I'm going to take this point, and I'm going to use my first cover, and I'm going to draw this separately. It's the same S1. So on this one, I'm going to use an angle theta, which starts at 0 here and goes to 2 pi here as you go around this way. And on chart 2, I'm going to put 0 here and 2 pi here. And then it's going to go that way, and I'm going to call that phi. Okay? So what I have in mind is that phi1, or phi and theta, take values from 0 to 2 pi. Actually, hold on. Oh, yeah, okay, sorry. Okay, so what I'm doing at this point is I'm labeling, and this is going to seem weird, but I'm labeling the points on this space, because we talked about, oh, I'm going to pick a point P, and then that point P has got to get mapped to somewhere. Well, I have to give you a way of telling you which point P you're talking about. Okay? So what I'm going to do is I am going to, and I know this is going to sound cheap, but I'm cheap, so deal with it. I'm literally labeling these points by this thing I'm calling theta, but I'm not coordinatizing it yet. And I'm giving these points a label phi, but it's not a coordinate yet. And you know it's not a coordinate because if these were coordinates, then I should not be including any values because the images have to be open. Okay? So, so here we go. So now I'm going to form 2 charts. That's just labeling the points. So now I'm going to form 2 charts as follows. I'm going to pick a chart U2, which covers sort of the top half and then a little bit extra. And then I'm going to pick a chart U1, which covers the bottom part with a little extra. Okay? Now, first of all, do these charts form an atlas?
Yes.
Yes, they cover the entire space. Okay? If I take the union of the U1 and U2, I've got the entire circle. But I also, in order to prove they form an atlas, I have to prove that the transition functions are differentiable. Okay, so we need to write down what the transition functions are. So first of all, for each of these, let me write down what the map is. So for U1, I'm going to have a map phi1, which is just going to be taking the value theta and giving me a value chi1, which is in R1.
Can we use just a different variable other than v, please, so that we don't, because we're defining our variable.
Oh man, you're. Okay, let me try and do this. So psi. Yes. Okay. So now my phi2 map, I'm going to define as psi goes to chi2, which is contained on R1.
Thank you.
Okay? And here's the trick, okay? So round about here is the value pi over 2. Doesn't matter which labeling you're using. You're either going pi over 2 up from the bottom or pi over 2 down from the top. Okay? But there's some overlap. Okay? So what we have in mind here is that the values of theta are going to be from, and let me write this down right. They're either going to be from pi over 2. So let me see. Theta is going from the top. And I want them to go a little bit. Hold on, I gotta. I don't want to just blindly copy down what I've got written. So the, yes, pi over 2 minus epsilon to 3 pi over 2 plus epsilon. Okay, so for the thetas and the u1, I'm actually using those values of the points. And then for the psi values, I'm using these for the U2 chart. Okay? So up here, the values of psi that go in here are just, again, pi over 2 minus epsilon to pi over 2 plus epsilon. Okay? Whew. Oh, sorry, 3 pi over 2. This is where it is so easy for me to get confused. Okay, so do you notice the magic of what I did? The labels that I gave here, this theta label goes from 0 to 2 pi, inclusive. I want to be able to label every point on the circle, but that's not like a nice open interval. And then neither is the label psi. There's no one label I can put on the circle that is an open interval that covers the entire circle, right? This is the root of why you can't cover the circle in one chart. Because to cover the entire circle, you've got to include either 0 or 2 pi. You can't leave them both out. So you can't do an open interval to identify all points. So that's fine. What we do is we allow ourselves to label points with a semi-open interval. It's open on one end and closed on the other. But when we use two charts, we use values of, say, theta in the chart where the values of theta that we're using form an open set. And similarly here. So in the actual coordinate maps that we're going to use, the region of R1 that we end up mapping to is open in both cases. So our charts are actually maps to open images in R1, which is one of our criteria. Okay, go ahead, Caleb.
So is part of the reason why we overlap the charts so that the transition...
Yeah, because we're going to talk about the transition functions in just a minute.
Okay, so...
But, well,
Because if they were just tangent, like you would have two open tangent sets, so that wouldn't be defined there, right?
yeah.
Okay.
Yeah, and this comes back to the question that you were asking. Somebody was asking about, or I was posing, like, could you just do two things that actually met? And if you tried to do that, then you'd run into the same problem, because if you didn't let these overlap at all, then to include every point in the circle, you would somehow be including a point which is at the edge of one of your charts, and it's all going to go sideways. Okay. So let me just make the observation, because we're almost there. I mean, it might seem weird to write this, but the map is really trivial. It just says the value of chi2 is the value of psi, where I'm only allowing this range of psis. And the value of chi1 is the value of theta, where I'm only allowing thetas in this range. It's the simplest map you could imagine. Like, I could do something more complicated, squared or something, but I don't need to. I can literally just identify these things. Okay? So, the map itself is so simple that we don't even need to think about whether the image is open. Okay? We don't have to worry about that. It's obviously open by construction. And whether it's one-to-one. So the things that we do need to check is that they form an atlas. So do the U1, U2 form an atlas? So do they cover all S1? Yes. Are the transition functions CP for some P? Okay. So to illustrate the transition functions, let's consider the overlap. Say the overlap on the right over here. Okay, so we're going to have the U1 and the U2. Okay, this point here would correspond to pi over 2 plus epsilon. And this would be 3 pi over 2 minus epsilon. And in this coordinate chart, it would be 3 pi over 2 plus epsilon and 3 pi over 2 minus epsilon. Okay. So let's see. So U1 is this guy, and this region corresponds to theta. Oh, I got these backwards. So this should be U2. This should be U2 and U1. Is that right? So in U2, or sorry, in U1, these regions are when theta's a little bit above and below 3 pi over 2. Okay, so in U1, I'm talking about a little bit above and below 3 pi over 2. But in this guy, this region over here is a little bit above and below pi over 2. Okay? Now, this is the range of coordinates that you map from U2 into Rn, and this is the range of coordinates that you map from U1 into. And so all we have to do is ask, well, how do I transition from these coordinates to these coordinates? And we can actually write down what that is. So the map that takes a point in the x1, which is where you map to from U1, and gives you back a point in x2 is nothing but this. There's your map. Let me make sure that's right. No, yeah, I think when I wrote my notes, I actually meant the other side, but let me do it this way. Let me do the transition function phi 2, 1, or phi 1, 2, phi 1, 2, 2, 1, 2, 1, 2. And now I think we're good. I have to remember to correct out my notes. Okay, so if I give you a point on the U2 chart, the coordinate value of that point in this overlap is some value between pi over 2 plus epsilon, pi over 2. I mean, you could pick any one of them. And then to map to the corresponding value that you would get from picking the point in the U1 chart and mapping it to R1 has to give you back an angle in this region. And clearly this map does that for us. Okay? You can similarly, and it doesn't have to be the exact same map, do the same thing over in this overlap. Okay? The transition functions are defined one overlap at a time. You don't have to do the same transition function for every overlap. Okay? Now that's our transition function. Is that P for some P? Yeah, what's the P? What's?
Infinity.
Infinity, good. I'm glad you didn't let me finish my question. Because it always gets bad when we talk about the degree of P.
A lot.
So yeah, it's a C infinity transition function. But guess what, folks? The circle, that's a smooth manifold. Like it's an infinitely differentiable manifold. And we actually just demonstrated that by explicitly constructing charts that form an atlas that's representative of the maximal atlas, studying the transition functions between the charts, and showing that the transition functions are C infinity. That's what you're going to do in your homework for a slightly more complicated example. Last but not least, and I'm not going to write anything, I'm just going to say it, many of you think about coordinate changes as something you do everywhere at once. Where you actually do that is when you have a space that you're working with, say you're starting with R2, that's where you have a space that is so trivial you can cover it with one chart. Call it U1. And that has a map, so it's a set of coordinates. But then what you can do is you can create an atlas by putting down another chart. U2, and that has a set of coordinates. And then the transition functions from U1 to U2 is just a coordinate change on your space. For us, though, we really just insist that these coordinate changes happen on the overlaps of charts. We don't need something as strong as this, because there's a lot of spaces that can't be covered with a single chart. Here's an example. Okay, all right, that's it for today. Sorry for keeping those final definitions and not just go through after the
Yeah, I don't know.
How much of that seemed familiar, Madison?